want to prepare something. I, I put some information together for you. I hope you enjoy it, and let me know if you have questions, or we want to have the questions at the end of the presentation. You let me know how you want to handle it. All right? So let's go. My presentation, I call it Heat Treat Furnace Fundamentals. And when we are in school and we were there, everything looks like, oh, yeah, I have to heat up a part of steel and hold the temperature required and then quench it. Easy. It's not that easy. The furnaces are very complicated, more than that, and it is better to understand why. So I'm going to show you some of the basic components of the furnaces that you may find, because not everybody has these opportunities of seeing the furnace actually working when we are in school. Okay, what we are watching here is the atmosphere heat treat furnace. This is the access door. This furnace works under atmosphere conditions. It is made for hardening steel, either on a neutral condition, hardening condition, or also for carburizing. There is a lot of systems involved in a furnace operation, and because of the atmosphere inside of the furnace, it is flammable. Then you have to have a lot of precaution, a lot of safety devices, and a lot of auxiliary systems helping to control the process and make it work. Okay, so talking about me, my name is Carlos Carrasco. I am a mechanical and electrical engineer with 40 years of experience in the design, construction, maintenance, sales of industrial furnaces, particularly on the heat treatment of steel or aluminum, expert in the design of combustion and safety systems. I am also former president and founder of the ASM Mexico chapter, and I offer specialized services and advice for various systems such as mechanical, electrical, control systems, safety, atmosphere, and combustion. I'm also a specialist in selection of furnaces, ovens, and various industrial processes. And I am a speaker, I'm a trainer, and I do represent several American and European companies down here in my country, Mexico. And we serve the industry, mostly automotive and aerospace, but we are not limited, of course. And this is a family company, a family business company who has started back in 65. So the next year, we will be 60 years in business. So we have seen a lot of systems, a lot of processes. I can I cannot tell how many manufacturing processes I have seen going from crackets, from manufacturing crackets, bread ovens to assemblies of airplanes and jet engines. So I have seen many things. Very, very interesting career I have. So the first thing we have to know about the furnaces when they are heated with combustion. Let's talk about combustion because that's a key point. So this British poet said the fire is the best servant, but what a master. When you fire the furnace has to be, it starts to destroy themselves because of the temperature. So you have to be always on top of the furnace and trying to control the deterioration caused by the by the combustion itself and the temperatures the furnaces are exposed to. And the first thing I want to talk about is about heat transfer. So what is the heat? I remember when I was in the school that my teachers used to say, "Oh, it is very easy. In a simple way, if the heat is the sum of the internal energy caused by the molecular activity." And I say that's not that easy, but eventually you understand. But the easy way to understand what is heat, where the heat comes from, it is temperature that you get in your arm when you rub your arm with your hand and you feel the heat. That heat is caused by the friction of the molecules of the hand and on your arm, and the decrease of the temperature of the skin is the heat. And that's exactly what happens inside the system. The molecules are agitated inside by an external source and then create the heat. Okay, there are different types of modes of heat transfer inside the furnaces, and there are mainly three. Conduction, which is transmitted from molecule to molecule direct by direct contact. I mean, only happens in solids. So they have to be contact, they have to be there. The other one is convection. The heat transfer process occurs between fluids and such as liquids or gases. And the third one is the radiation. That's the one transmitted in the form of light and not always necessarily visible, like the one we have from the sun. It is important when you have to select the furnace, and this is a experience we have every day. I just heard yesterday a problem like this. The furnace was not properly selected because depending on the temperature is how the heat transfer is going to occur. Conduction is only direct contact of the molecules, but convection happens between some temperatures, lower temperatures, and radiation happens at higher temperatures. Convection it's based on square velocity of the speed and the mass of the speed moving around the load, and radiation depends mostly on the area exposed to the heat source. So depending on the load you have, like we have here, let me check my laser. So when you have this furnace, and these are the burners represented here, and you have different loads, like this one very low, and this one not so low. So you can have like a high velocity burner. This is what you see here is a high velocity burner who can deliver high speed gases at high temperature. And for high speed, I'm talking about 90 feet, 900 feet per second. So they are very high. But this velocity enhances the heat transfer to the load. So it is important to understand what type of load I have, what temperatures I am going to work, and what is the requirement by the process. Perhaps I cannot use direct fire like in this slide, but there are some other options when you have indirect gas firing, and you can avoid the presence of oxygen inside the chamber, of the heated chamber of the furnace. So it is always important to understand what process do you want, what's your material, what's your requirement. So be careful when you do that, because remember, it's like every day, every single day, we see that the furnace was not properly selected. In the graph you see here, because in the furnace I have, like in the previous slide, I have the heat source by radiation, let's say, because of the temperature of the flames, but also have the convection created by the high speed of the furnaces. So the heat transfer in the furnace by conduction moves like this because it's slower. It just goes by molecule to molecule, as I say. But also the radiation goes faster. Yeah, and the combination of radiation and convection is much better always. And always we always are going to depend on the effective emissivity of the load and of the walls of the furnace. So when we always are watching how much volume do I have inside the furnace, because when I fire a burner, depending on the capacity in BTUs per hour or kilocalories per hour, the volume that I deliver inside the furnace, when I make my calculation, how many gas, how many air I am going to use, these are going to be expanded inside the furnace for about 3 times. If the furnace is small, the flames are not going to be contained inside the furnace, and you will see flames coming out for the fumes and even from the fumes the chimney, the fumes exhaust of the chimney, and also from the doors. So the engineer, when select the furnace, when you are selecting the burners, you always have to decide what's the best size of the furnace, how much volume I need inside to accommodate my load, number one. What is the spacement I have to put between loads? Because when it's radiation, as I mentioned before, the radiation is based on the exposed area of the material. the more the more area I can expose to the heat, the faster is gonna be the heat treatment. So I have to consider now the load, the size of the load, the weight of the load, so I can make my heat balance and determine how much heat I have to put into the load. Then I have to consider how much volume I have to keep inside to have a properly sized furnace. Not too big, not too small. Then when you talk about, I need, give me a second. I think I'm using like, hold on 1 second. Something happened here. No, no, it's okay. It's okay. I just put it in different. No, it is, I'm sorry for that. This slide should be here. Sorry for that. I was working late night yesterday. Sorry for that. So when when I am sighting the furnace, I need to know what's the temperature of the furnace and what's the temperature of the other surface, like in the load. And then I understand how much heat transfer I am going to have inside the furnace, or how much heat I am going to lose inside the furnace. In the furnaces, when we design the furnaces, I have these combinations of materials, properly selected, properly manufactured, the insulation materials to stand the heat on the hot face of the furnace, and also to make able to drop the temperature across the section, the cross section of the insulation, to have a temperature safe for the operation, and also a good look for the ambient inside, outside the plant. So in the furnaces, you always have to calculate the heat losses. You know, there is a power, net power that I have to deliver to the furnace. So when we make the heat balance, we work backwards in our calculation. So I need to calculate how much heat I have to deliver to produce a certain amount of mass or load into the system. Then, depending on the type of furnace, if it is a box furnace or if it is a continuous furnace, the design of the furnace, the temperature of the furnace will let me know how many losses of heat I have to the openings, like if it's continuous furnace, or if it's a box furnace with a door, and how long do I have to open the door, close the door to load or unload the furnace, or if it's a slot furnace, when like in a forging operation, when the opening is always there and I have continuous loss of heat through that opening. Depending on the temperature, I will be selecting the type of materials, as I was saying, the type of material and the thickness of the material. So I can understand how much heat is going to be lost across the walls to have a safety operation. If the furnace in some cases has water cooling systems like fans or shafts or some other devices, walking beams are very common that are water cooled. Then I need to understand that that water is going to draw heat from my furnace, and I have to consider that also. The furnace is continuous, then I have a conveyor that goes all around, all across the furnace, carrying the load across the furnace, and then it will cool down, and I have to reheat it again every time it goes again into the furnace. So conveyor and fixture losses. Sometimes I have to put the load in a fixture that was not considered is not considered as a production, but it will be considered in the heat losses of the furnace. If the furnace is like in the video I show, like if the furnace is protected, the load is protected with atmosphere, that atmosphere is going also to require heat because it is supplied at low temperature, like at 70 Celsius degrees. So the atmosphere has to be heated up so it will absorb heat from the furnace. Then with also the furnace is gas fired, then I have a lot of heat losses through the flue gases to the exhaust. And I have to calculate that losses. And it will depend on the efficiency of the system. The more efficient the system is, the less heat losses I am going to have. Then I am able to determine how much heat the process needs, the heat, the furnace heat, and all the losses I have to overcome that losses plus heating up the load. And I will be able to determine how much is the thermal or the power fuel I need to put into the furnace. That is why I say I have to calculate backwards how much heat and how much fuel at the beginning of the process I have put inside of my furnace. The higher the temperature in the furnaces, the higher the losses and the lower the efficiency is going to be in a system. There are when I have combustion, direct combustion, I have to measure the fuel gases at the exit of the furnace. And depending on the temperature of the fuel gases and the combustion control I have, then it will be able I will be able to know the the efficiency of how much heat I'm going to lose in that during that heating process. When I have perfect combustion, when all the fuel like natural gas, let's say, and the air are combined, and I burn all the oxygen with all the hydrogen inside the burners, then I have perfect combustion. Unfortunately, that doesn't happen like very often. Sometimes, and for design, I have to add additional air because there are not everything burns in the first section of the burners. You know, when you are burning, and you will see a video about this, when you burn inside in the right on the nozzle of a burner, you have a very high activity, and you can burn the gases inside there. But what is not being burned there, it will be burned in a second stage and probably a third stage of the combustion process. So most of the time, the engineers will design combustion systems. We add like a minimum of 10% of additional gas, of additional combustion air to burn the excess of fuel that has been burned during the process. So the more air I add, I have zero here, I have 10 here, 20, 50, the lower the efficiency is in the furnace. In a regular combustion direct fire system, the maximum efficiency I can achieve in a furnace, it will be around 30%, unfortunately, because like a forging furnace, it needs high temperature. I need a lot of heat and a lot of a lot of a lot of heat is lost during the process because if the fuel gases are high in temperature, and I have to add excess of air for the process. These kind of furnaces are very inefficient. Modern furnaces, modern burners, like recuperative burners, regenerative burners, can achieve up to 75% of efficiency, but it's not always easy to apply for all the operations. So there is not one furnace, not one burner for all the applications. At the same way, there is no one furnace for the same application. You have to select different furnace for different application by different heating system. We are talking about combustion, but it can be heated by electricity. We are not talking here about electricity because actually we don't have too much enough time for doing so. Then, when I preheat the air, the combustion air is mainly 20% of oxygen roughly, and the rest is nitrogen. So the nitrogen doesn't have any involvement in the combustion process, but I have to heat that mass of nitrogen, so I lose efficiency. So the burners manufacturer decided that we can preheat the combustion air, then I will be more efficient and I will be using better my energy inside my furnace. So if the flue gases are again here, and this is the percentage of available heat, the more I heat or preheat the air, the more efficient I can come into my process. So as you can see here, there is a lot of information for the furnace. For the furnace design, there is a lot of information, but it's not like in one book. You know, it's like it's spread out in very different sources such as book, catalogs, and manuals of the burners itself. And you have to be able to find out where do I found it? When can I use preheat combustion air? I am going to do it because also preheating the air costs money because the material has to be stainless steel. These materials they have stand higher temperatures and become more expensive. And me as a furnace manufacturer, the price, the selling price of a furnace is always something I have to be aware of because I cannot sell the most perfect furnace because it's not going to be competitive. So I have to keep a balance between how much I want to use in good materials and how much is going to be good enough to sell the furnace to my potential customer. There is also information on fuel saving, use preheating air with a 10% of excess air in the furnace. So the temperature of this is in Spanish, I'm sorry. So the temperature of the combustion air in Fahrenheit is shown here on top. And on the other side is the temperature of the fuel gases, and so depending on how much you heat up the combustion air, are the saving of fuels, and you can find it here. So way in advance when we are designing a furnace, or when we want to retrofit a furnace in a combustion system, we can always do something before changing, before expending the money. We can make the calculation. We can approach to the right people and ask, I want to do some fuel savings. How can we achieve that? And then starts a complete investigation and research how to do that. There are also softwares actually that you can punch in information of the furnace, the process, the temperature of the process, the actual fuel heat capacity of the fuel, the altitude of the systems also is something because you are almost at the sea level, and I am living at 22 and 2,200 meters above the sea level. So the air, the available oxygen in the air is different here than it is down there at the sea level. So all these factors affect in my calculation of air for the combustion. Okay, so the more dense the air is, the less mass of air I'm going to need, and the thinner the air, the more mass I need to manage into my system in order to compensate that that lack of oxygen because of the altitude. Okay, so if we talk a little bit about combustion, the combustion reactions are here shown if I use carbon as a heat as a fuel plus oxygen, not pure oxygen, the one I have in here, or if I use hydrogen. Always in the combustion system of hydrogen and oxygen, I am going to get steam, water, and heat. That's perfect. When I have this is the best I can do in my process. Sometimes the systems are not able to do that, so I have incomplete reactions when I have some byproducts of the combustion plus heat, and these are generating less heat in the system. Less heat is released either by having less oxygen or having excess of oxygen into my system. In all cases, I will not be able to get the total amount of heat that the combustion system can release. So having a good a good combustion system design, good valves. Each valve is a specific design. There are valves for controlling the air. There are valves for controlling the gas. When you have this properly selected, you are going to have a good combustion. What you are going to see in this video is a burner firing just a tunnel of air with a huge fan recirculation to dry cloth that is dampened in latex to manufacture wheels for the cars. Okay, so these got a big burners running there, 6 millions of BTUs is a lot of heat, and you can see it here. At the top of the video, you see the flames are very. I'm sorry for the quality of the video because I shot it right there into the plant. So the in the top of the video, you see the flame is very blue. That's why the ratio and the combination of air and combustion and fuel are better than the way it is in the extreme of the flame. I'm going to put it again. Here is like more red because this is the excess of air of fuel that was not burned at the beginning of the process. And because I have this damper open, I let air introduce it into the system and create different colors and different reactions during the process. But I think it's a good explanation of how the combustion happens inside the furnace when you are having this type of heating. Okay, when you are in the furnace, as I mentioned, I always have to measure the temperature of the fuel gases, but I also have to read the components of the combustion. So from the heat, I say that we have to have water. I will have CO2. I have hydrogen. I have free oxygen. Maybe I have a different combination, even free um, natural gas here, methane. So in this section, when I am able to deliver the perfect combustion in theory, it's when I can burn 1:10 ratio of one volume of gas and 10 volumes of air. So this is when the complete combustion happens. When I have this, the excess of air into the system is zero. Okay. When I have the efficiency of air, then I am going to start. So in this side to the right of the graph, I am going to start having higher values of oxygen and higher values of CO2, and the sample from my flue gases are going to be wet, much more wet, depending on where I am. Or if I have excess of air in the right side of your of the graphic, then I am going to have free hydrogen. I am going to have more water. I am going to have CO2. So it is important when you are firing a furnace to have this instrumentation to understand this kind of graphs, to know where are and how efficient your system is. The new uh, heat analyzers look like this, and they give you a lot of information. Not only the free oxygen or CO2, they also give you the NOx, because we are always concerned about the NOx that we generate during the combustion process. So the new instrumentation lets you not only the NOx, the oxygen, the carbon, but also the efficiency of your system. And the combustion system has to be at least checked every month. Every month you have to check, because the vibration of the systems of the furnace, of there are machines around the plant. The combustion blower is used to get out of balance and create a vibration that makes the valves to lose the adjustment. So every 30 days, technicians or the engineers at the plant has to check the combustion in their system. Okay. Then another important and very important thing in the energy efficiency of the furnace is the insulation lining. Okay. There are different ways to isolate the furnace from the heat, either to use a bricks, back it up by a board, let's say, it can stand less temperature. Most of the time we can we can we use a combination of bricks that can stand either high temperature or mechanical abuse, because sometimes the load can hit the walls, or those high speed burners that I was showing you are very aggressive to the surface, because they try to they're very abrasive to the surface. So we have to decide if we am going to use a hard brick, or I can use insulation brick, which is softer and more expensive, but it's better to isolate the heat from the inside of the furnace. How I'm going to anchor the bricks to the walls, because they will expand. You can see here this line here. And here, this is expansion provision. So the materials will expand, but it will not fail during the heating time. So also during this talk, we are not going to provide detailed information about the refractory systems. It is appropriate to have some knowledge about the insulation and refractory. The refractories are meant for the heat and the mechanical abuse by the process, and sometimes chemical abuse also. Because when we are talking about a melting aluminum melting furnace or a forging furnace, the the scale created by the process itself, it's very aggressive chemically to the to the bricks, of the furnace, and it has to be properly selected for that. Of course, there are many options that the vendors, the suppliers, the people who design this can let you know what do you need for a particular application. If you are using, let's say, aluminum melting furnaces, you need high alumina, high alumina, like 90%, 99% of alumina into the bricks that can stand the aggressiveness of the aluminum in the process. The way you install the furnace is also a completely different technique. So the turbine lining are divided mainly into ones. Insulation, they are lighting, they are more porous. So because they are more porous, the granulation size of the materials allows to have air inside, and this air acts as an insulation. So remember, I told you the transfer occurs by contact. So when I have these big grains inside of the insulation, there are less contact, more air, so they can isolate the heat better. Okay. Usually they are used to back up the furnace to beyond the refractory limits of the material. The refractories, they are directly exposed to the interior of the furnace or the oven. They are dense than the insulation, and they are designed for working in temperatures or above 530 and 538 Celsius. The insulations work at 538 and above that, then you have to start using refractory. And it can stand temperatures probably in the range of regular in the range up to thousand and more thousand Celsius degrees for a heat treated operation. Not for melting. Melting of steel is a different kind of animal. So the technologies to install the insulation of the furnaces changes depending of the application and the materials that are going to use. In the other slide, we were watching bricks. In this slide, we use these refractory anchors, and then we cast the insulation or the refractory into the furnace. It is a concrete castable made of insulation materials or refractory materials. So it depends on the applications. Sometimes the applications are different, and I can use what is called ceramic fibers. When I use ceramic fibers, I need to understand that I'm going to be, because it's very porous, I can isolate very well the heat from the outside of the furnace. There are different techniques to make like they call modules like this, and the modules can be anchored to the walls of the furnace in a different ways. I have anchors like this. I have um, sorry, I forgot what the name it is in English. I have this part of ceramic that holds the anchors and the blankets into the furnace in a better way. So depending on how you put it, it's gonna be a wall or it's gonna be a roof. Is the way you select, and there are different types of uh, ceramic fibers from medium to high density, depending on the temperature that are going to be exposed. Also, the ceramic fiber is very good to isolate the the heat from the furnace when it's discontinue operation. When you open the door, also the the ceramic fibers tends to lose a lot of heat when you open the door. So yes, the furnace isolated with ceramic fiber can be heated up very fast. But if you open the door to remove the load and reload the furnace, then you are going to lose a lot of heat. So this is something you have to take into consideration. The inertia heat of the furnace. You want it to cool it down during the the loading process, or you want to keep that heat inside the furnace so you don't lose production time between loads. So there are options, and again, you have to consider what do I need, what my process needs, and then I have to think about it. And then are also graphite insulation in vacuum furnaces. And now I'm going to make a big change from topics that we are talking. Insulation can also be graphite. In this vacuum furnace you see here, this is a vacuum furnace used for heat treatment. The graphite felt, I have used different densities of graphite felt here inside the furnace, or in the aerospace industry, the materials used for these applications cannot see carbon during the process, so graphite is forbidden. And then the insulation is made just with molybdenum. So all the furnace is isolated by molybdenum shields. Very expensive, but and very fragile once you heat it up the first time. But it is what the process needs. So as I was saying in the beginning, all depends on your process, your materials, and your requirements. What type of insulation you are going to need, what type of heating you are going to need, and what type of furnace you are going to need. So different furnaces, different applications, different materials, different temperatures. A vacuum furnace like this regularly can stand temperatures up to 1,300 Celsius. So I'm going to jump to one to these new technology furnaces. You know, the heat treating in vacuum technology, which is like a trend, is what it is in the industry all over the world. See? So the vacuum treatment process consists of heating metals parts in pressure and atmosphere evacuation from the closure by mechanical means. So I have the vessel of the furnace, and I have pumps that evacuate the atmosphere inside the furnace. Depending on the materials and the porosity, the roughness of the materials, it will accumulate impurities, dust, bacteria, oils from preview process like cutting process, you know, and the furnace, all these impurities can be removed by vacuum, because actually the vacuum furnace remove molecules from the material, and when they come out from the furnace, they are very clean. Mm. The vacuum furnace are capable to controlling the pressure, the temperature, and a very close range. Compared to the atmosphere furnace, I have to control the temperature and the atmosphere quality inside the furnace. And now in the vacuum furnace, I have to control the amount of the vacuum furnace inside, which means how many molecules I have inside. The higher the vacuum level, the less molecules I have inside the furnace. Brazing is one of the processes that you can run in a in a vacuum process, in a vacuum furnace, but also sintering, heat treatment, deposit, and degassing can be done under vacuum. So there are many applications in the industry for the vacuum furnaces. Controlling the vacuum furnace is easier than controlling the conventional atmosphere furnace. In an atmosphere furnace, I introduce an atmosphere that is rich in hydrogen. It also has nitrogen, traces of oxygen, because I do generate this atmosphere in a separate equipment and introduce it into the furnace. You know, sometimes it's just pure gases, introduce it into the furnace. But anyhow, I have to read that gases inside the furnace and see what is happening, and then add different gases and control the amount of the proportion of those gases inside and the oxygen present inside the furnace. So I don't have to carburate my parts. I have to make it brighter depending the process I am doing. In a vacuum furnace, as long as it's well sealed, the doors are okay and all the connections are sealed. There are not impurities inside the furnace that is running on a level of 10 minus 3 torr or 1 micron, which approximately equates the dew point of minus 73 Celsius, which is a number very used in the controlled atmosphere furnaces. So in the vacuum furnace, I just do the vacuum into the furnace, evacuate the furnace, and then I can start heating the process and heating out the loads. And because there is no contaminations inside, there is no pressure, I can heat up more evenly and more accurate. And more important for the industry, I can repeat the process one time after another. The main systems in the vacuum furnace are the pumping system, the heating system, the control system, and the cooling system. It depends 100% uh, on this on these systems. This is a cross section of a vacuum furnace. When you can see the control panel is in the back. I have a cooling fan in the rear part of the furnace. I have the power free through these furnaces are electrically heated 99% of the time. There are some manufacturers who use gas combustion furnaces, but are not very popular because the temperature cannot be higher than compared to electricity. So I have inside the furnace, I have this, which is called the hot zone, when all the heat is happening. And in the back of the furnace, I have a heat exchanger. So I load the furnace. This is the door. Hinge it. I open the door, put the load inside the furnace, close the door, evacuate with my pumping system the furnace, and heat it up with a previous recipe that it is established by the process. As I mentioned at the beginning, it's not like, oh yeah, I have to heat it up and then hold the temperature and cool it down and that's it. No, because in the real life, the materials has cross sections that I have to be aware that I don't have to, I have to manage, but not, I don't want to crack any part because they are very expensive. So I have to create recipes when I have to heat up, hold a lower temperature, then I have to slowly heat it up again, and then I have to hold the temperature sometimes 3 times, like H13 steels requires things like this. Machine parts requires a lot of step for heating. Once the load is at temperature and all the stove temperature is happening, this furnace has a hatch in the back. It opens and the furnace is back with nitrogen. Most of the time with nitrogen, at high pressure. The furnace, when it's open, is at 1 bar of pressure at atmosphere pressure. But when we close it, we can pressurize the furnace up to 6, 15, even 25 bars. The higher the pressure, the higher the speed I can quench the part. So the more pressure I need, and the more pressure I put into the furnace, the higher the higher speed I can have to achieve the cooling rate required for certain materials. And the different materials needs different cooling time and cooling rate. The vacuum furnace can also control the cooling rate. It's not always like going all the way down. They can go down, wait a little bit so the core of the load achieve the same temperature of the surface of the furnace, and then I can cooling again. In the back of the furnace, the hot gas of the hot nitrogen goes through a heat exchanger and it's moved. The heat exchanger is connected to an external water system I will show you. And then the fan moves the nitrogen back, cooled nitrogen back to the heating zone through a nozzle which are 360 degrees arranged around the sun to cool the part evenly. So in the vacuum furnace, the distortion is controlled much better because I heat up in a 360-degree uh, mode, and then I cool down again at 360 degrees. So vacuum furnaces are very good to control the distortion inside the furnace. What you can see here is not noted. This is the vacuum pumping system. Then the the um, the muscle of the vacuum furnace is the pumping system. I have a high vacuum pump diffusion who can go up to 10 minus 5 millibar, and then have another pump, low pump, that can go up to 10 and 3 millibar, and then have a mechanical pump. So the three pumps in conjunction are the ones in charge to evacuate and control the vacuum level inside the furnace. This furnace, you can see, is not so big. They're bigger than this, but the diffusion pumps are commercially available in 40 inches in diameter, and can pump out at the speed of 190,000 cubic feet per hour. So they're very, very high. And in evacuating the furnace, and actually they can draw from the furnace molecules. If you put inside a material, it will draw the materials, the molecules from the load. Inside the furnace, there are different configurations of the hot zone, which is also the heart of the furnace. We have the hot zone where the load is connected inside. Heating elements are here. The insulation is here. Everything contained in this mid steel structure that can be square shaped or can be rounded. So this is the hot zone, and this is one of the important parts of component of the vacuum furnace. The cooling system, as I was explaining, use nitrogen, or can you use argon or helium, depending on the speed rate I have. Of course, when you use argon or helium, is more expensive the process because of the rareness of the gases. The gas is cooling in the heat exchangers of the back of the furnace, and the recirculation fan goes send it back to the load and back again through the heat exchanger. This furnace require keep the vessel of the furnace. This line is a water jacket. The furnace is cooled by water with this jacket, and also requires softened water. Outside the furnace, this is my furnace, this is the heat exchanger I was showing you. So I have a complete sealed tank and a cooling system that goes to it depends on the location or where I am, but I have another heat exchanger which is only used to cool the water coming from the heat exchanger of the furnace. Configurations are different, sizes are different depending on the application. Sometimes we use cooling towers, sometimes we don't. It is totally dependent on the location and the application. So this is the reference I have for this talk I presented to you. As you can see, many information I have comes from the ASM. So I don't want to miss the opportunity to make a commercial. Become members of the ASM. It's the largest association of professionals and students with all kind of information about materials and processes, not only heat treatment. And thank you for the companies that I work and provide me with materials for. So thank you very much. This is me. And if you have questions, I'm here to listen to you guys. Do you have questions?
Excuse me, Carlos. If we
Yep.
ask about the hot zones, why it's there's round and square, or the difference between round and square, and the purpose of being different.
This is a debate that always happens. In my experience, the square zone are more used in Europe, and in America, round square. Different suppliers have different opinions on how fast can you heat in a round square, and how much you can heat up or cool in a square zone. Basically, the square zone allows you to load bigger loads, to put bigger loads inside the furnace. That's for sure. The round square have limitations on that. But the hot sun, the square hot sun, has bunks who open and close during the cooling system, during the cooling process. That's something you avoid totally on around hot sun. So it depends on the application, and I don't see many hot suns, square hot suns in my area.
Okay, thank you.
Mhm.
Which one is less polluted, regenerative or recuperative?
Pardon me, can you repeat?
Which one is less polluted, regenerative or recuperative?
Sorry, the line is breaking. Can you repeat it again? I'm sorry.
No problem, no problem. Which one is less polluted, regenerative or recuperative?
Oh, it is. It is. It is. The furnaces are different applications. Depends on what you are looking for. You know, um, sometimes you recuperate the gases. Sometimes you do not recuperate the gases. Depends on what you are doing. The furnaces that works with helium, you can recuperate the gases. Usually, the nitrogen is not being recuperated.
Thank you.
And we ask about the parameters determining the material used in the furnace, the heat exchanger. What the main parameters? It's all just thermal properties, or there is mechanical ones.
It is the heat exchanger inside the vacuum furnace. You mean it's a copper thin tubes, and sometimes depends on the manufacturer. The fins are extruded into the from the tube, so there is no weldings, and there is more contact between the tubes and the fins, and it's more efficient. Some others are braced to the tube, but all the heat exchangers are made out of copper. Inside the furnace, outside the furnace, they are made out of aluminum in the outside cooling system. Just like the radiators in cars, they are like that in the external ones. All right. So if you don't have more questions, I would like to thank you for the invitation to participate, and I hope you like the talk